Hey guys, so welcome back. So what we want to do today is look at a few practice calculations using the ideal gas law. So hopefully with these you can kind of get an idea of why this formula is so important to us and in what situations we will need to know it or need to use it. And if you, so turn to assignment 4 first. And if you look at the bottom, the different forms of the ideal gas law are given for you. This is the standard form that we will use most often, but then there are two other forms that we derived in the last video, one that involves mass and molar mass, and the other that involves the density of a gas. And then you have some ideal gas constants given down here. The one that we talked about in the last video, as well as the one that will be used in these problems, is the 0.0821 liters atmospheres per mole Kelvin. But there's also some different values, 3.814 liters kilopascals per mole Kelvin and 62.4 liters millimeters mercury over mole Kelvin. Okay. So this is a situation similar to when you had standard temperature and pressure. You can really plug in a multitude of pressures in that situation. You can use 1 atmosphere, 760 millimeters of mercury, 101.325 kPa, because they're all equivalent. So the same situation applies here. All these R values are equivalent, but again, we want to choose the one that allows the units in our problem to cancel out. So just keep that in mind. And you could always use 0.0821. That's one that really all you need to know. You just have to make sure that all the values in your problem have proper units. So volume has to be in liters, pressure has to be in atmospheres, and then temperature, of course, has to be in Kelvin. So let's look at a couple of these problems together. The first is, what is the pressure in atmospheres exerted by a 0.5 mole sample of nitrogen gas in a 10.0 liter container at 298 Kelvin? Okay. So again, keep in mind, we have to remember this, that the 22.4 liters per mole example that we talked about in the previous videos only applies at STP. And unless a problem tells us that there are 22.4, unless the problem tells us we're at STP, we cannot use that number. So in this situation, we have standard temperature, okay? Actually, we don't. We have 298, so we're at 20 degrees Celsius, so that wouldn't apply anyway, okay? But you could check and see how many liters we have in this mole. So we would have about 20 liters per mole here, so that wouldn't work out. So we're trying to solve for pressure. So if I look at the standard form of the formula, PV equals nRT. What I want to do is go ahead and solve for pressure. So P equals nRT over V. It makes it a lot easier if you go ahead and do your algebra first, isolate your variable, and then plug things in. So now we can plug in. So our number of moles is 0.500 moles times the gas constant, R. So I have liters. I want my answer in atmospheres. My temperature is already in Kelvin, so I use 0.0821 liters times atmospheres over mole Kelvin times temperature. So it already put it in Kelvin, so 298 Kelvin. So it's important to remember that Celsius must be converted, but they already did that for you here, so no need to worry about that. Divided by the number of liters. So the number of liters in the problem is 10.0 liters. So now we can check my units. Moles cancels moles, liters cancels liters, Kelvin cancels Kelvin. We're left with atmospheres, which is what the problem asks, so we're in good shape there. Type in the calculator, make sure you get this number. We have 3 significant digits here, 3 significant digits here, 3 digits here, so we round our answer to 3 significant digits. Okay, so we look at the next one. What is the volume in liters of a 0.25 mole sample of oxygen gas at 20 degrees Celsius and 0.97 atmospheres of pressure? Okay. Before we solve this one, again, I just want to make sure we're clear on the distinction between using the ideal gas law formula here versus what we did with the combined gas law formula in the previous chapter. The combined gas law formula only worked when I had a sample of gas and I already knew things about it. I knew its pressure, temperature, and volume, and I changed one of those things and I calculated how the other variables responded. This formula, the ideal gas law, allows us to solve for an unknown variable. Okay, so if we know the pressure, temperature, and volume, we can solve for the number of moles. We don't have to simply solve for a before and after change there. Okay, so I ask you for the volume, so we can go ahead and do the algebra, rearrange the ideal gas law. So we'll get V equals nRT. Okay, so then, divided by P. Okay, so then we can just go ahead and plug in there. Okay, so we have N is 0.250 moles times R. So I check my problem. I have atmospheres, I have moles. I'm going to have Kelvin when I'm finished, so I can use the 0.0821. So 0.0821 liters times atmospheres over mole Kelvin. And then temperature. So the best way to mess this up here is to forget to convert to Kelvin, so we can't do that. So we have to add 273. So we have 293 Kelvin divided by 0.974 atm. Okay. Then I want to go back and double check myself, check my units. Kelvin cancels Kelvin. Atmospheres, moles, I'm left with liters. That's what the problem asked me for, so I'm probably in good shape there. Go back and check the problem. 3 significant digits, 3 significant digits, 3 significant digits. So I round my answer to 3 significant digits, and you get 6.17 liters. Okay. So that's 2 examples of just the basic ideal gas law calculations. Should be very easy to you when they're just set up like this. You basically just take the formula, do one-step algebra, solve for the unknown variable, plug in, make sure units are straight, and you're in good shape. So let's look at 2 that are a little bit different. Number 3 says what mass of chlorine gas in grams is contained in a 10-liter tank at 27 degrees Celsius and 3.50 atmospheres of pressure. So there's really 2 options to solve this. The first option is the longer option. There's more chance to make a mistake, is we could actually go and say, well, if we solve for the number of moles of chlorine gas, I could always do one-step stoichiometry afterwards. And hopefully that occurred to you, that we could just do that, do PV equals nRT, solve for N, find the number of moles, then convert moles of chlorine gas to grams of chlorine gas, and we'd be in good shape. That's perfectly fine. Or the other option just kind of basically combines that step. So you have PV equals mRT divided by capital M for molar mass. So you'll still be doing the same thing with the numbers. This just combines kind of the stoichiometry step, the mole to gram conversion with the ideal gas law. Okay. So I will use this formula and go ahead and solve that. If you want to go ahead and use the first version of the formula, solve for N, and then do a stoichiometry step when you're done, that's perfectly okay. You will get the same answer there. But I'll do it this way. So I'll do my algebra. M equals PV, capital M, divided by RT. So little m is the mass, capital M is the molar mass. So I know the molar mass because I know the identity of the gas, so I can add that up. Okay. So then I can plug in. So I have 3.50 atm, that's my pressure, times my volume is 10.0 liters, times my molar mass. Chlorine gas is Cl2, so don't forget that it's diatomic. So 70.90 grams per mole, divided by the ideal gas constant. So I have to figure out which one to use. So I look at my units. I have atmospheres of pressure, so I can use the 0.0821 liters times atmospheres over mole times Kelvin. Then I have my temperature. I get 27 degrees Celsius. Don't forget to convert that to Kelvin. So you have 300 Kelvin there. Okay, so I go back in, check my units. Atmospheres, liters, Kelvin, moles. I'm left with grams. Okay, so let's stop for a second and see if that's even logical. Is that what I'm looking for? Yeah, I'm asking you for the mass of chlorine. I solved for the mass variable, so it makes sense that my answer should come out in grams. Okay, So you have 3 significant digits, 3 significant digits, 3 significant digits. So your final answer should be rounded to have 3. Okay, so you have 101 grams as your final answer. Okay. So let's try one more of these. Number 4, at 28 degrees Celsius and 0.974 atm, 1 liter of gas. And the S got left off. That has a mass of 5.16 grams. What is the molar mass of the gas? Okay, so we're going to use the second form of the ideal gas law. Because we have a mass, we need to solve for a molar mass. Okay, so if we write down just the kind of the standard version of that, we have PV equals little m, which is mass RT over big M. And now I'm solving for molar mass. So I do my algebra and solve for capital M. So capital M molar mass equals MRT divided by PV. Okay, so now I can plug in my numbers and solve for the molar mass here of my gas. Okay, so the mass of the gas is 5.16 grams times R. So I have my pressure in atmospheres, so I can use 0.0821, 0.0821 liters times atmospheres per mole times Kelvin times my temperature. Got to convert my temperature to Kelvin, so I will have 301 Kelvin divided by my pressure, so I have 0.974 atm times my volume, 1.00 liters. Then I go back and I check my units, so I have Kelvin cancels Kelvin, liters cancels liters, atmospheres atmospheres, but the grams and the mole don't cancel. So is that going to be an issue for us? Well, let's think about it. Grams here times per mole, so moles in the denominator of this unit, so our final units would come out to be grams per mole. So let's stop and think, is that logical? Is that realistic? And yes, hopefully you should realize that's what we're trying, that's what our unit should be. If we're solving for molar mass, it should come out in grams per mole. So if you go through and look at your problem, 3 significant digits, 3 significant digits, 3, 3. So we round our final answer to 3 significant digits. So your final answer should be 131 grams per mole. Okay? So I couldn't necessarily ask you outright just to tell me out of thin air what the identity of this gas is, because there's several gas molecules that could have a molar mass of 131. But I could, however, give you a multiple choice list and ask you what the identity of this gas is. So I could give you, xenon, krypton, argon, neon, and ask you what is the identity of this gas. And then you would just match up the molar mass of the gas with the molar mass you selected. Okay. So if that problem ever arises, I might not ask you what the molar mass is. I might just ask you to pick from a list what is the identity of a gas. So you'll have to keep in mind and realize that the molar mass in the problem we solve for and the molar mass of the gas is what we'll try and match up there. Okay. So hopefully that's pretty straightforward for you. Just be sure you select the right formula. Make sure all your numbers are in proper units. Don't forget to convert to Kelvin. Make sure you choose the proper ideal gas constant. Make sure your units cancel out. Make sure you get the desired units at the end. Otherwise you went wrong. Okay. So go ahead and do this independent practice. I think there's only 11 of them. They should be pretty easy. Shouldn't take you too long. Even if they seem easy to you, go ahead and do them. Do them all. They're really good practice, and they're really important because in the next video, we're going to start combining this with other things. So if you don't have a good grasp on this, it's going to be extremely difficult when we start combining it with other things.